Welcome back. In the previous video, we have discussed how to solve the one-dimensional heat equation with different boundary conditions using the finite difference approximation. And in this video, we are going to do similar things, but with the wave equation. And as a first example, let us look at the one-dimensional wave equation with Dirichlet type boundary conditions. So for the space variable, we assume that x is between the interval 0 and L. And here we are saying that for the boundary condition, the displacements at the boundary points x equals 0 and x equals L are always 0. And the following method will work for general boundary condition of the Dirichlet type, where you can specify, a value alpha and beta here. But for simplicity, let us, apply this 0 condition as an example. We also have two initial conditions, since here the derivative about t, highest derivative about t is 2. There is theory that illustrates the existence and uniqueness of a solution under reasonable conditions of f and g and these boundary conditions. But here we're not going to show you or prove any theory regarding to the theoretical existence of solutions of the PDE problem. However, you are going to see in our approximation in the numerical method that why these conditions could help us to generate a unique value at a discrete grid points. Okay, so we use the same notation as before in terms of the grid points. So in the xt domain here, we have discretized the space variable from 0 to L as x0, x1, x2 up to xn, where the step size for the space variable is delta x. And we have also discretized the time axis as this grid, where we have the step size for time is delta t. So here would correspond to t0 equals 0. And in the next time step, it will be t1 equals delta t. And here will be t2 equals 2 delta t, for example. And all the way up to some t, for example, capital K, that we would like to get the values at all locations. So use the same notation. U and K is U at xn tk. So since we have already familiarized ourselves with this kind of notation in the previous video, let us just derive the finite difference approximation to this equation using these kind of notations. So let us calculate UTT using the finite difference approximation at every grid point xn tk. And this is equal to U at xn tk plus 1 minus 2U xn tk plus U xn tk minus 1. So we have three different tk values here, divided by delta t squared, since we are using the second, approximating the second derivative. And this is equal to c times uxx, right? C times uxx also at the point xn tk. We have u at xm plus 1 fixing tk minus 2u at xn tk plus u xm minus 1 still at time step tk divided by delta x squared. Okay, so now let us do some algebra and try to relate the value at time step tk plus 1 to other values. So after this algebra, you'll get this equation. K minus 1, this will be a minus actually, plus some constants, which will be c times delta t divided by delta x squared, then times these three values, right? So it will be un plus 1k minus 2unk plus un minus 1k. So let us look at the figure and see what we have derived. So the value unk plus 1 is a combination of four values, which is this un 2 times this unk minus un at time step k minus 1 and plus some constant, which we can call lambda. So if we call this lambda times a combination of three values, which is un plus 1k minus 2unk plus un minus 1k. In other words, the value unk plus 1 can be determined by values of two previous time steps. One is three values at time step k and one value at time step k minus 1. So let us also summarize what we have, what values we have from the boundary conditions and initial conditions. Similarly, as in the case of heat equation, with the Dirichlet boundary condition, we have at x equals 0 for all time step t, these values here. So the red points values are known. And similarly, the values are and these red points are also known by this boundary condition. So we have u for x0 for all time step, here is 0, and u for the right boundary point at all time step k is 0. This is for all k. And similarly, as in the initial condition of the heat equation, we also have the initial values here at time step t equals 0, which is this. So in particular, for time step 0, for all xn, we have f of xn. In other words, the values at these blue points are also known. So let us look at the recursion formula and see what values are lacking in order for us to use the recursion formula to generate all the values on this two-dimensional grid. In particular, if we would like to calculate this value, using this recursion formula, we will need four values. So to calculate this value, we will need four values. This value, this value, this value, and some value that is not on our discrete grid, right? So in particular, for this fictional grid, it will correspond to actually t minus 1 equals minus delta t. Let me actually write on the other side. So here will be t minus 1 equals to minus delta t. Of course, time cannot be negative, but let us pretend if there were a little tiny step minus delta t, what these values would be. If we have this value, then one can use this recursion formula to get this value by these four values. So there's way to estimate this value by making use of the other initial condition. So we also have the ut at time equals 0 is equal to g of x. So let us try to apply the central difference formula for this initial condition. So we have ut x0 is equal to g of x, and then using central difference formula for every xn at time t equals 0, we have that u xn 0 plus delta t minus u xn 0 minus delta t divided by 2 delta t, since we're using, this is a first order derivative, is equal to g, of course, at xn. So now we have obtained a relation between the u values at any xn on the first time step and the fictional time step minus delta t. Let us do some algebra and then write down the specific relation. So using this shorthand notation, we have this un minus 1 is actually equals to 2 delta t times g of xn so let me write it down again. So this is un minus 1 here at time step minus 1 time step minus 1 2, here maybe time step minus 1 for xn. So this is un minus 1. We have, then this will be equal to this minus 2 delta t plus times g of xn. So it will be u1n minus 2g of xn times delta t. Okay, so we have a relation between these values and these values. And since it works for every n, so this equation is about the relation between this value and this value, this value and this value, this value and this value. Okay, so now let us plug in this relation to the recursion formula for the points on the first time step. So in particular, we can apply the recursion formula to time step t1, which corresponds to k equals 0 here. So then we have un at 1 is equal to 2 un 0 minus 2 minus un minus 1 plus lambda times un plus 1 0 minus 2 un 0 plus un minus 1 0. So in other words, we are just applying the recursion formula to the points on this row for every xn. Okay, and since we know, for example, this value will be related to this value, we can plug in this kind of equation to this equation. Minus then un1 minus 2 gxn delta t, and copy the rest, right? So okay, so if we observe this equation, we see that there are un minus 1 on both sides of the equation. So it is a little bit different than the case, if you recall, in the heat equation, where once we plug in the equation obtained from the boundary condition, we have an explicit formula for the points for the points near the boundary. But here we have to solve actually for this un1. So we can just put this rearrange this term to the left hand side and solve it. Once we solve it, we actually have, so let me directly write down the equation after we solve it, since it's very simple. So un1 will be actually un0 plus gxn delta t, then plus a half lambda un plus 1, 0 minus 2 un0 plus un minus 1, 0. Okay, so now we have eliminated the value on this fictional grid by this equation and have solved for these values. So in particular, this value will be determined by these three values only. And this value will be determined by these three values only. So we have a recursion formula now to determine the values at time step, the first time step, delta t. Okay, so let us now summarize everything in the left hand side. So this is 0. So in particular, now we have determined the second row by this recursion formula. And as discussed earlier, for other points, we can use the recursion formula derived directly from discretizing our equation. So for example, this value will be determined by these four values. And this value will be determined by these four values, right? So using these conditions, we can determine every value on this discrete spatial time grid. To implement this in MATLAB, you can store everything in a matrix, right? And the initialization will be in the first row we have all the values from the initial condition at time step t equals 0, so 0, 0, u0, 1, u0, 2, all the way to u0 n minus 1, u0 n, etc. And then, as in the heat equation, you also have the boundary condition. So you have at x equals 0 times step 1, x equals 0 times step 2, all the way to a specific time step of your interest, right? 0 at time step capital K, for example. Similar for the right boundary point, un time step 1, un time step 2, all the way to un at time step capital K. These values are determined by the boundary condition. These values are determined by the initial condition related to this one, right? So now let me call this recursion formula star and this recursion formula star star. What we have described on this part is that we can apply the recursion formula star star to determine the second row and similar second row here. In particular, we're saying that, for example, u x1 at first time step will be related to these three values and using this recursion formula, right? You will be, we don't need the values of the on the fictional time grid. And then this value will be determined by, three values here, and so on and so forth. Once we have, the values on the first two rows, in other words, the u values of the first two initial time steps, then we can use the values, we can use the recursion formula star, where we can calculate, for example, ux1 at second time step by these four values, right? So we can determine this value by three values, nearby values of the previous time step and one value of the two time steps earlier, right? So in particular, this value is determined by this. Sorry, I made a mistake. This value is determined by these four values. Okay, so what we have said for now is that once we have the initial value, boundary value, and these two recursion formula, we can generate every value in this matrix. So we have obtained a numerical solution for this PDE problem. There is similar stability condition as we have discussed in the case of the heat equation. So the condition for the wave equation is as follows. The constant lambda, which is c times delta t over delta x, should be less or equal to 1. So in other words, we should have this inequality between the spacing in time and spacing in space. In other words, we cannot choose a large time, a very small spacing in the space variable, but a very large time step. So we should choose a time step smaller enough so that it satisfies this condition. Of course, we don't like to choose a very small time step so that it takes forever to generate a numerical solution. But at least we should know the time step to be at most this constant. Okay, so now let's talk about the example where we specify Neumann boundary condition to the one-dimensional wave equation. And again, we have two initial conditions. So the idea would be very similar. So first we can discretize our equation using the same finite difference formula. So we can again apply the central finite difference formula to UTT and also to UXX, but with respect to T and X respectively, right? So we can just copy the discretization. Okay, so now we have the discretization of the equation. And also, for the initial condition, it is the same. So we can actually have these values just like before. So in other words, we have u at time step 0 for all n is equal to f of xn. And we also have this initial condition, which would generate a similar recursion formula for the points at the first time step with respect to the points for time step 0. Right? In other words, this value can be determined by these three values. This value can be determined by these three values. So again, we have this recursion formula for the first time step. So let's do it once again. It's not working, so let me write it down. Let me try it again, actually. Okay, so now what we are lacking is the values on these boundary points here and here, right? We don't have the Dirichlet boundary condition where the values, the U values are specified on the left boundary point and right boundary points for all time t. So if you recall, in the case of heat equation, we have a fictional grid on the left boundary points, near the left boundary points, and a fictional grid on the right boundary points. So we can apply the central difference formula to these two Neumann boundary conditions. So in other words, let us do that really quick again because it's the same as in the case of heat equation when we have the Neumann boundary condition. So for example, for the left boundary point, partial u partial x at 0 t is equal to 0. Then we have u at 0 plus delta x at time t minus u at 0 minus delta x at time t divided by 2 delta x is 0. And in other words, we have u delta xt is equal to u minus delta xt. And if we apply this to every time step tk, then we have u for the first time step, for any time step k, for delta x is just x1 is equal to uk minus 1, which are the value on this fictional grid, right? In other words, this value is equal to this value, this value is equal to this value. Exactly as in the case of the heat equation where we have similar Neumann boundary condition. So in other words, now we can estimate these values. For example, this value will be determined by this value will be determined by these four values. But once we have this value, we have that value, right? So again, one can implement this as follows, that at the other boundary point, minus 1k and plus 1k. So this value will be same as this value will be same as this value. In other words, once we have the first two rows and these conditions, we can determine every value, including the value on the boundary points. Let us look one example again. If we would like to determine this value, then we will need these four values. But one can actually get this value by values of the previous two time step. Once we obtain this value, we can use this kind of relation to get this value, and then we have all the four values needed to proceed to the next time step on the boundary. And for all other points, we can use the exact recursion formula. Okay, and so of course you can, like in the case of wave equation, to determine a specific recursion formula for these boundary points by plugging these values to the recursion formula and obtain a different value. So in either case, you can generate all the values un, xn, tk, right? To implement it, one can again store everything in a big matrix. So now let us use a larger matrix to store the fictional grid as well as here and as here. So since we have not plugging these values to the corresponding recursion formula, let us choose to store these values as well. Just as an example, you can do it the other way. So we have at time step 0, minus 1, time step 0, 0, time step 0, 1, time step 0 at x2, all the way to n minus 1 and time step 0, n time step 0, and un plus 1, which is the fictional grid near the right boundary point, right? Again, this value will be determined by the initial condition, and this value will be determined by this kind of equation. This value will be determined by this one. So we have the first row already. So we have here the u minus 1, 0, and u 0 and plus 1. And then one can use the recursion formula star star for the second row as discussed in the previous example. So we can use star star to generate all the values from here to here. In particular, this value can be determined by 3 values as discussed here. So un is only related to the locations n, n plus 1, n minus 1. So here is n minus 1, here is n plus 1. And also this value can be determined by these 3 values. This value can be determined by these 3 values, so on and so forth. So now we have all the values u0, 1, u1, 1, u1, u2, 1, etc. all the way to un minus 1 times step 1, un1. And once we have these values, then one can use this relation to get the fictional grid u minus 1 and un plus 1. So in particular, with this value, you can get u minus 1, 1, and with this value, you can get un plus 1, 1. So now you have the first 2 time steps. And again, you can use this recursion formula. Sorry, you can use this recursion formula to generate the values on the next row. So now you can use star, for example, to get u0 at time step 2. You can use four values, right? So the four values are these 4, right? And you can do the same. Once you have determined every value all the way up to un2, then you can use this value to determine this value by this relation, and so on and so forth. So basically, using 2 for loops, you can generate all the values in this matrix using the information specified here. So in the implementation, you only need to specify a few values, in the first row, and also these values, right? So the stability condition is the same. Again, it doesn't change whether you are using applying the Neumann condition, boundary condition, or the Dirichlet boundary condition. You should, when you choose a spacing for delta x, you should choose a delta t accordingly small enough to satisfy this condition, so that your numerical scheme could generate a reasonable solution that is that will converge to your theoretical solution. So this concludes our discussion for the solving the one-dimensional equation with different boundary conditions, and hopefully you know how to combine the techniques to solve, for example, the more general Dirichlet type of boundary condition, or more general Neumann type of boundary condition, where, for example, here it's not 0 but some other function alpha of t or beta of t. Basically, you use the same difference formula, but here it's not 0 but some but specified by some function alpha or t. Or you know how to implement mixed boundary conditions, where at left point you may have Dirichlet, or but on the right point, boundary point, you have the Neumann type. Then you can, at one boundary point choose the fictional grid, and at another one you can just use the Dirichlet boundary condition. So thank you for your attention.